by z, z minus 1, z minus 2. So z minus 1 will cancel z minus 1. Put 1. If I put 1 here now, we are going to have put 1, 4 minus 3, 1. Put 1, 1 times, put 1, minus 1. That's minus 1. Right? 4 minus 3, 1. Put 1, 1. Put 1. Yes, that's 1 minus 2. This one has cancelled out. So according to the theorem, what is the sum of the residue now? This is the first residue, this is the second residue. So I'll say summation R, the sum of the residue is the first one, and the second one, 2 minus 1, is equals to 1. 2 minus 1 is equals to 1. So the integral will be equals to what? 2 pi I times summation R. I don't want to claim the theorem, so the sum of residue is 2 minus 1, 1. So the integral of f of z is equals to 2 pi I summation R. That's 2 pi I times 1. That's 2 pi I. Simple. So let's integrate C of z squared divided by z minus 1 all squared times z plus 2 dz. What's the part where C is equals to, C is such that absolute value of z equals to 3. So the same way, integral of z squared divided by z minus 1 all squared, z plus 2. Okay, so sketch this. Well, I'll just sketch it here. Z equals to 3. It means that the circle is centered at where? Centered at 0. Radius is what? Radius is 3. So this is the contour. Label y and x. Find the pole. The pole will be at where? Z minus 1 all squared, z plus 2 equals to 0. Or if I equate this one to 0, this one will give me z equals to 1. What's the order of this one? Of second order. If I equate this one to 0, this will be a simple pole, z equals to minus 2. Now, z equals to 1. Will it lie within the contour or it will be outside? Z equals to 1. 1 will be here. Z equals to minus 2. Oh, that one too will be here. Good. So the two pole will be within C. This is C. So we now find the residue at each of the pole. So residue of 1. Residue of 1. Because 1 is pole of second order. And how do we find residue of second order? 1 over n minus 1 factorial will differentiate. So that's 1 over 2 minus 1 factorial d dz. Because it is dn minus 1 and our n is 2 here. So the 2 minus 1 will be this d1 of z minus 1 all squared times f of z. F of z is z squared divided by z minus 1 square z plus 2. We are taking the limits. Let me put the limits. Limits as z approaches 1 of all these jargons. So z minus 1 square cancels z minus 1 square. 2 minus 1 is 1. Limits as z approaches 1 d dz of z square over z plus 2 now. So we differentiate z square over z plus 2. These two are gone. How do we differentiate this? Quotient 2. What is the quotient 2? Give this one square, z plus 2 all squared. V du. V is z plus 2. Du. Differentiate. This is 2z. Minus u. Z square. Differentiate this one 1. So at where? We are taking the limit as z equals to 1. You can open the bracket. This will be 2z square. Yeah. Plus 4z minus z square divided by z plus 2 all squared. So 2z square minus z square. That's z square plus 4z divided by z plus 2 all squared. limit at z approaches 1. If I put 1 plus 4, this is 5. 1 plus 2, 3. 3 squared, 9. So the residue of this one is 5 over 9. Then we also take the residue at z equals to the other pole, z equals to minus 2. So residue at z equals to minus 2. This one is simple pole. So the residue at z equals to minus 2 will be limit at z approaches minus 2 of z minus minus 2. That will now be z plus 2. F of z, these are f of z, z squared divided by z minus 1 all squared z plus 2. You observe that the residue at a point. So the point you are taking the residue. So that point will always cancel out. So z plus 2, z plus 2. So we are taking the limit at z equals to minus 2. So put minus 2 here. Minus 2 all squared 4. Minus 2 minus 1 minus 3. Minus 3 squared 9. So the first one is 5 over 9. The second one is 4 over 9. So what is the sum of the residue? Because the two poles, they are within the contour. So what is the sum of the residue? The first residue is 5 over 9. The second residue is 4 over 9. So 5 over 9 plus 4 over 9, that is 1. And according to Cauchy theorem, so this integral, let's say f of z, is equals to what? 2 pi I times sum of residue. That's 2 pi I times 1. That one too is also 2 pi I. So that is how to apply residue theorem. So we have many examples. Now, number 4. If I want to integrate c sin z divided by z raised by 6 such that absolute value of z equals to 2, what will be the answer? How will I start? Dz. So I want to integrate around a contour whereby z center at 0 and radius is 2 of this function sin z divided by z raised by 6. So sketch the contour now. The contour centered at 0, radius is 2. This is the contour. Fine. And what is the pole? The pole is when z raised by 6 equals to 0. We already know that if z raised by 6 is 0, z equals to 0. Of which order? Of 6th order. But it won't make sense for me to start differentiating. How many times? 6 times. Okay, 5 times. So we can use another way of, we can take our residue in another pattern. So z equals to 0. Z equals to 0 is within the contour. Then we take the residue at z equals to 0. How will I take the residue of this stuff? Sin z over z raised by 6. So I will use the third approach by taking the Laurent series of sin z and divide it by z raised by 6. The one that gives me 1 over z, the coefficient of 1 over z, is my residue. So z equals to 0 now. Go to your Laurent series. So want to take the residue of sin z divided by z raised by 6. I'll first say 1 over z raised by 6. Then I'll expand sin z. So sin z will be alternating. That's z minus z cube over 3 factorial plus z5 over 5 factorial minus, z6. So z5 over 5 factorial minus the next one will be z raised by 7 over 7 factorial. I think I've gotten what I need. Yeah. And so on like that. Then we do what? We multiply by over z6. If I multiply by over z6, that will be 1 over z5. So minus 1 over 3 factorial with z cube. z5 over z6, this one will be plus 1 over z with 5 factorial. And so on like that. So what do I need? I need the coefficient of 1 over z. So the coefficient of 1 over z is, so we need coefficient, that's our residue, coefficient of 1 over z. So the coefficient of 1 over z is what? 1 over 5 factorial. This is the coefficient of 1 over z. And 1 over 5 factorial is 1 over 120. So, and according to that theorem, integral of sine z divided by z6 dz is equals to 2 pi I summation r. So, it's only one pole. So, that is 2 pi I times 1 over 120. So, 2 take care of 120. That's pi over 60 I. Pi over 60 I. So, let's integrate e raised power zt divided by z square plus 1 all square dz, where c is such that absolute value of z is equals to I. Absolute value of z is equals to I. Yeah, e raised power zt, yes. Put plus or minus I. So from here now, the circle is centered at 0. Radius is what? I and minus I. It means that we are taking the radius along imaginary axis. Let's say this is plus I and the other one here is minus I. So this will be our radius. So I'll just put my contour like this. It will pass through I and minus I. So after that, y and x, because z centered at 0, radius is I, that is 1 on vertical axis, and minus 1 like this. So what is the pole? The pole will be at where? The pole will be at z squared plus 1 all squared equals to 0. Now, so let's carefully factorize this z squared plus 1. Z squared plus 1 on its own is like z plus I, z minus I, right? And all squared, it means that these two will also have squared like this. So equals to 0. Z squared plus 1 is like z plus I, z minus I. And then we have z squared plus 1 with square again. It means that these two factors will also have squared. So I now equate these two to 0. If z plus 1 all square equals to 0, it means that here, this one will give me z plus I all square equals to 0. Z will give me minus I. And what is the pole of this? This is pole of second order, because I'm having plus I in two places. And for the second one too, if z minus I all square equals to 0, that will give us z equals to what? I. That one too is a pole of what? Second order. If you're having pole of second order twice, okay, so z equals to minus I is here. Yeah, is within the contour. Z equals to I is also within the contour. So we take the residue as the two pole, assuming that one has exceeded that circle now. So we will not consider that one again. So residue of the first one is residue of minus I. So pole of second order we differentiate. So residue of minus I, it will be 1 over limit. It will be limit as z approaches minus 1. So I'm trying to make sure that I applied all the properties of residue in each integral. This one now, we use this one for Laurent series. The first one, simple pole. This one or residue of nth order. So it will be limit as z approaches minus I times 1 over 2 minus 1 factorial, because we are dealing with second order here now. 1 over 2 minus 1 factorial d what? d2 minus 1 over dz2 minus 1. That will be d dz, because we are removing 1. Of what? I'm considering this one first. Z minus I. It will be z plus I all squared times the function. This is the function. E raised power zt divided by, instead of putting z squared plus 1 all square, I will just change it to this so that it can cancel out. So z plus I all squared, z minus I all squared. So in that case, this z plus I will go. So 1 over 2 minus 1, that's 1. We are now taking the limit as z approaches minus 1, and the derivative with respect to z of e raised power zt divided by z minus I all squared. So how do I differentiate this? Quotient rule as usual. So if I want to use quotient rule now, carefully, this one will have square. That will be z minus I. It's already carrying raised power, so this one will now be raised power 4. V du, write V, z minus I all square, differentiate e raised power zt, that's t e raised power zt minus u dv, write e raised power zt, differentiate z minus 1 all square. Of course, that will be 2 times z minus I. So we are also taking the limit at z approaches minus I. So can we, is there anything we can do? No. So just put z equals to minus I at z, not at t. So it will be, if I'm putting minus I here for z, minus I minus 2I minus 2I all squared. That's what? Minus 2 squared, 4. I squared is minus 1. This will be minus 4t for this one. If I'm putting minus I here now, this will be e raised power minus it minus 2 e raised power, put minus I here, minus it, put minus I here, minus I minus 2I. With this, to turn to plus 2I, but 2 and 2I will give me 4 now. This will be 4I. Yes. Divided by z minus I all square. If z equals to minus 1, minus I minus 2I. Minus 2I all raised power 4. 2 raised power 4 is 16. I raised power 4 is 1. This is over 16. But let's check again. If I put minus I here now, minus I minus 2I minus 2I all squared. Oh, minus I minus 2I minus 2I all squared. This one will be 4I squared. And I squared is minus 1. That's minus 4t e raised power zt. Z equals to I e raised power minus it. So here now, put z equals to minus I minus 2I. Minus 2I times minus 2 minus 4. Oh, minus 2I times minus 2, that's plus 4. Plus 4I. Yeah, it's not cancelling. So we got it. So can we factorize 4? If I factorize 4 into brackets, I e raised power minus it minus t e raised power minus it all over 16. So 4 here 1, 4 here 4. Good. Then take the residue at the other pole. Okay, so this is a residue at z equals to minus I. So the residue at z equals to I, because both I and minus I, they are within the contour. So that's that one too is a pole of what? Second order. So we now also take the limit as z approaches I, 1 over 2 minus 1 factorial, differentiate. Here our z equals to I. If I bring this one to this side, that will be z minus I all squared, that's second order, times f of z. Our f of z is e raised power zt divided by z plus I all squared, z minus I all squared. So z minus I will take care of z minus I. 2 minus 1 is 1. We are taking the limit as z approaches I of the derivative with respect to z, e raised power zt divided by z plus I all squared. So how will I differentiate this? Same way. So we did the previous one. Quotient 2. We are going to have z plus I all raised power 4 v du. V is z plus I squared. Differentiate this. Differentiate e raised power zt with respect to z. It will be t e raised power zt minus u dv now. Write e raised power zt. Differentiate z plus I all square. That's 2 times z plus I. 2 times z plus I. At where? We are taking the limit. At z approaches I. We are taking the limit as z approaches I. So it means that all the things that are here, z, put I. If z is I plus I, 2I. 2I all square. That's minus 4. Because I square is minus 1. 2I all squared. Yeah. So minus 4. This will be minus 4t. Put z equals to I. E raised power it. Or put z equals to I minus 2 e raised power it. Put z equals to I plus I, 2I. Multiply by 2. It will now be 4I. Right? All over. Put z equals to I plus I, 2I. 2I, all raised power 4. 2 raised power 4 is 16. I raised power 4 is 1. So divide both sides. Sorry. Or factorize minus 4. Because minus 4 is common. If I factorize minus 4, that's minus 4 times t e raised power it plus I e raised power minus it divided by 16. So 4 here and 4 here, for that's minus t e raised power it minus I e raised power minus it divided by 4. So this is the second residue, this is the other residue. So what is the sum of the residue now? The sum of the residue is the addition of these two. That's I e raised power minus it. Let's cut it to 4. Minus t e raised power minus it. Let's cut down to 4. And this minus t e raised power it over 4 minus I e raised power minus it all over 4. So collect like term. The one with e raised power it, e raised power minus it, e raised power minus, all this one are, sorry, I plus it. So summation R will now give us the one with e raised power it. Okay. So if I divide e raised power minus it and e raised power it. Okay, the one with t and the one with I. Yeah. So if I take these two and I pair these two as well. So we are going to have I over 4 e raised power minus it minus t over 4 e raised power it. Okay. And the one with e raised power minus it, let's say plus, okay, that will be minus t over 4 e raised power minus it plus I over 4 e raised power it. So the sum of R, yeah, that's summation R. And the residue theorem. The residue theorem is an integral of f of z dz is equals to 2 pi I times summation R. So multiply everything here by 2 pi I. So integral of c f of z is equals to, if I multiply this one by 2 pi I, multiply I over 4 by 2 pi I. So let me say, if I multiply this one by pi, this one will be I square will be minus 1. Right? If I multiply this one by 2 pi I, 2 pi I, 2 pi I. So I square will be minus 1, 2 over 4, that's minus pi over 2, right? E raised power minus it. Multiply this one by 2 pi I minus pi over 2 t e raised power it. You now get a pattern that you know that sine, let's say sine theta, that one will be e raised power I theta minus e raised power minus I theta over 2, something like this. Okay. And if I multiply this one by 2 pi I, that will be minus pi over 2 I e raised power minus it, multiply this one by 2 pi I plus multiply by I here, this one will be minus pi over 2 e raised power it, e raised power it. Okay, so in that case we are done. But if I want to transform my integral, my solution into trig form, you can actually factorize pi over 2 from here. If I factorize minus pi over 2, this one will remain e raised power minus it. And if I factorize pi over 2 from here as well, minus minus plus e raised power it. Yeah, the one with t, factorize pi over 2 from here as well. This will be minus pi over 2 minus pi over 2 minus pi over 2 t. So this one has t. Yeah. So I factorize pi over 2 pi over 2. Sorry viewers. So from here, to reduce the confusion, because it will be somehow confusing, separate the one with t and the one with I. Sorry, if I separate the one with t and the one with I, so some of the residue will be this one has I, this one also has I. So if I factorize I over 4, this will be I over 4 minus e raised power it. This one will now be plus, right? E raised power minus it. Yeah, I'm pairing these two. And if I separate the one with t, that will be minus this one. Minus, Abby. And this one will be minus, Abby. Good. Then if I separate the one with t over 4, minus t over 4 into brackets e raised power it plus e raised power minus it, right? So the sum of the residue is equals to minus I over 4. What is e raised power it minus e raised power minus it? Go back to our Euler identity. Sine theta is e raised power I theta minus e raised power minus I theta over 2i, right? Yes. Over 2. So if I cross multiply, so e raised power I theta minus e raised power minus I theta will be 2 sine theta. So from here, we are going to have 2 sine t, because here our theta is t, 2 sine t, minus t over 4, e raised power I theta plus e raised power minus I theta. That will be 2 cos t. So 2i, yeah, it's true, 2i sine t. This is 2 cos t. So 2 here 1, 2 here 2. So sum of the residue will be I square minus 1 with minus, that's plus 1. This will be 1 over 2 sine t. 2 here 1, 2 here 2, that's minus t over 2 cos t. And what is the residue say? We multiply by 2 pi I. So our solution is integral of f of z is equals to 2 pi I multiplied by half sine t minus t over 2 cos t. So multiply this one by 2 pi I, 2 cancel 2. This will be I pi sine t. Multiply this one by 2 minus 2 cancel 2, I pi and t cos t. You can factorize I pi. So that is the solution of this problem. So that is how to use a residue theorem in evaluating integral on complex variable. Now, another application of residue is integration around a unit circle. So whenever we are given any problem, let's say we are asked to integrate from 0 to 2 pi f of sine theta and cos theta d theta. So any function that involves sine and cosine, and we are integrating from maybe from 0 to pi or whatever boundary. So the first thing is that we convert, let me say, the algorithm. Number one is that, so we convert sine theta and cos theta to exponential I theta. So using relationship between sine theta as exponential I theta minus exponential minus I over 2. And then from there, we assume that let z equals to exponential I theta. So from there, we've transformed the integral from real plane to complex plane. So example, I have just 2 examples on this one. So integrate from 0 to 2 pi 1 over 5 minus 4 sine theta d theta using residue theorem. So integrate from 0 to 2 pi 1 divided by 5 minus 4 sine theta from 0 to 2 pi. So from here now, this sine theta that is here, we say that, recall that sine theta is equals to exponential I theta minus exponential minus I theta over 2i, right? But what we are having here is what? 4 sine theta. So 4 sine theta means I'll multiply everything here by 4. If I multiply by 4, it will be 2 over I into e I theta minus e minus I theta, right? Multiply by 4, 2 cancel. So substitute back into the integral. So we're having integral from 0 to 2 pi 1 over 5 minus 4 over 5 minus 2 over I into e I theta minus e minus I theta. Let me put that the theta here. The theta. Okay. So we now say that let exponential I theta, let's call it z. That's the second step. So let exponential I theta equals to z. If I differentiate with respect to theta, so dz over the theta is what? Differentiate exponential I theta. It will be I exponential I theta, right? And what is exponential I theta? Is z. So dz d theta is equals to what? Iz. The z d theta equals to Iz, because if z is equals to exponential I theta and I differentiate, I'll still have I theta, and that's z. So we are now having integral. So the integral will not be from 0 to 2 pi again. It will now be around C, a closed curve, because we've transformed from real to complex plane. So it will now be integral around closed curve 1 over 5 minus 2 over I into bracket z, because exponential I theta is z, minus exponential minus I theta. So if exponential I theta is z, exponential minus I will be 1 over z. The theta, from here if I cross multiply, so the theta will be dz over Iz. Cross multiply and divide both sides by Iz. So we are now having integral around the closed curve 1 over multiply, open the bracket with 2 over I. So we are having 5 minus 2 over Iz minus 2 over I times 1 over z. This will be 2 over Iz like this. Multiply by dz over Iz. So clear the fraction. If I multiply through, like this side, if I multiply through by Iz, because Iz is my LCM here. So integral of this one will be 5Iz. Multiply this one by Iz. Iz will cancel. This one will be minus 2. If I multiply 2 over iz by iz, oh, it will be 2z squared. Multiply 2 over iz by iz, that's plus 2. We're having 1 over. And then, don't forget, that iz that we are using to multiply, it will go up like this, right? Times dz over iz. So what happened? Iz cancel iz. So we are now having integral of dz over minus 2z squared plus 5iz plus 2. So how do I move from here now? That is where my residue will now come into play. So from here, we'll now go back to our residue theorem. So how do I use residue from here? I'll find the pole. Now, because I forgot to mention that we are integrating around the circle, it means that our z, or z, is always 1. Like the radius of the circle is always 1. So z is always 1. Here now, c is such that z is equals to 1. So what is the pole? The pole is when this denominator is 0, when minus 2z squared plus 5iz plus 2 equals to 0. When this stuff is 0, solve for z. Use quadratic formula. Z equals to minus b plus or minus b squared minus 4ac divided by 2. We've done that one in complex number. So z equals to 2i and I over 2. These are the solution of this. Z equals to 2i and I over 2. Now, since what is it called? The contour is a circle centered at 0, radius 1. So the contour is a what? Is a circle centered at where? Centered at 0. Z is always 1. Centered at 0, radius 1. It means that this is how our contour will be. Now we are having pole 2i. What's the meaning of 2i? Y is minus 2. So y equals to minus 2. So 2i will be here. Because if this one is 1, this one is 1, this one will also be 1. 1, 1. You get? So 2i. The other one, I over 2. That's like 1 over 2 on y-axis. So 1 over 2 is like 0.5. So that I over 2 will be around here. So it's only, according to that Cauchy theorem, according to that residue theorem, it's only this I over 2 that is within this closed curve C. Then we only take the residue at I over 2. So in order to do that, so the residue of z equals to I over 2, this is simple pole. It will be the limit at z approaches I over 2 times z minus I over 2 f of z. This is our f of z. Our f of z is 1 over. So instead of me writing all these jargons, I'll just factorize this. So 1 over, if I factorize this, this will be like z minus 2i. Factorize this, or z minus I over 2. So what will happen? I over 2 will take care of I over 2. So we now take the limit as z equals to I over 2. So our answer will be the residue at z. So the residue at z approaches I over 2. It will be 1 over, if I put I over 2 here now, I over 2 minus 2i. So here you can use your calculator or just do it and rationalize. So the residue will be 1 over 3i is equals to 1 over 3i. So according to residue theorem, the residue theorem says that after we find the residue, the integral of this stuff, integral of cf of z dz is equals to 2 pi I times sum of the residue. That's 2 pi I times 1 over 3i. So I cancel I. So our answer is 2 over 3 pi. 2 over 3 pi. Again, the algorithm is that from here, if it is sine, you change sine to ei theta minus zi minus I theta over 2. That's step 1. Substitute for sine theta here now. Here we're having 5 minus 4 sine theta. That's 5 minus 4 into all this stuff. We arrive at this point. And then the transformation, the next transformation is let e raised by I theta equals to z. Let e raised by I theta is z. You differentiate. By differentiating e raised by I theta, we are going to have I e raised by I theta. And then from there, we are having from 0 to 2 pi, the integral will now be from 0 to c, or we are integrating around the closed curve c. So we arrive at this part, use residue theorem here. Find the pole, take the residue at each pole, and then obtain the sum of the residue. So the last example, now let's evaluate from 0 to 2 pi dx over 2 plus cos x using residue theorem. So we start by transforming this cos x. We say that cos x is equals to what? Exponential ix plus exponential minus ix over 2, right? If it is sine, sine is exponential I minus exponential minus I over 2i. So we are now integrating from 0 to 2 pi dx over 2 plus exponential ix plus exponential minus ix divided by 2. So is there anything we can use to take care of these two? If I put over 1 here now, we are having integral from 0 to 2 pi 2 4 exponential ix plus exponential minus ix dx over, where you are going to have something like this, which is integral from 0 to 2 pi 2 over 4 plus exponential ix minus exponential minus ix dx. So after that, we now say let exponential ix equals to z. So in my previous example, we are dealing with theta. So let exponential I theta equals to z. So let exponential ix equals to z. If I differentiate z with respect to s, so dz dx will be what? I exponential ix. And then exponential ix is z. So dz over dx is equals to iz. So this integral that is moving from 0 to 2 pi, it now goes along c. It will now be like this. We are now integrating along c, such that we are having 2 divided by 4 plus exponential ix is what? Is z. Exponential minus ix is what? Oh, sorry, this is plus. So exponential minus ix is 1 over z, because if exponential I is z, I put negative here, that's 1 over z. Dx, so dx will be dz over iz. So if I multiply the denominator by z, so we are going to have integral of this part will be 4z, right, plus z square plus 1. Then that z will go up. We are going to have 2z here times dz over iz. So z will cancel z. I is a constant. Let's regard I as a constant. So we are having 1 over I integral of okay, don't let me take I as constant. Multiply this denominator 2 by I. So this will be 2 divided by 4iz plus iz square plus I dz. So from here, we are now going to apply our residue theorem. So by doing what? We solve this to find the pole. The pole will be at where? The pole will be at iz square plus 4iz plus I equals to 0. So if we solve that, so we are going to have z is equals to well, it can be difficult for calculator to press I, because we are having I here now. So let's take that I out. No, let's take that I out as a constant, so that we are going to have z squared plus 4z plus 1. So z is equals to, using quadratic formula, z is equals to minus 2 plus or minus root 3. Minus 2 plus or minus root 3. Don't forget, we are having 1 over I. outside. So like I said earlier, whenever we are integrating around the circle, absolute value of z is always equals to 1. Is always equals to 1. So what is the contour? The contour will center at 0 and radius is 1. 1 minus 1. So this is how the contour will be. This is the contour. And then the pole. The pole are minus 2 plus root 3 and minus 2 minus root 3. So what is minus 2 plus root 3? Minus 2 plus root 3, I think that one is less than 1. Sorry, it's less than minus 1. That one will be around here. Because this is minus 2 plus root 3 and minus 2 minus root 3. The other one now, minus 2 minus root 3. So that minus 2 minus root 3 is definitely greater than, sorry, it's definitely less than minus 1. So let's put that one here. This is minus 2 minus root 3. This is minus 2 plus root 3. Because root 3 is around the 0, 1 point something. And if you subtract minus 2, so it will be around this edge. So it's only this pole. It's only pole z equals to minus 2 plus root 3 that is within the contour. So the residue at this pole. So the residue at z equals to minus 2 plus root 3. It will be what? The limit. The limit as z approaches minus 2 plus root 3 times z minus this. That will be z. Bring this one plus 2. Bring this one minus root 3, right? F of z, because the limit is on z minus a times f of z. So f of z, this is our f of z. 2 over this stuff. Well, we've already factorized it into z plus 2 minus root 3 and z plus 2 plus root 3. And in that case, this one will cancel. So we are having the limit as z approaches minus 2 plus root 3 of 2 over z plus 2 plus root 3. So if I put z as minus 2 plus root 3 here, that's 2 over minus 2 plus root 3 plus 2 plus root 3. So minus 2 cancel minus 2. Root 3 plus root 3, 2 root 3. 2 divided by 2 root 3. That's 1 over root 3. And don't forget, I is working. I is working. We are multiplying whatever we are getting by 1 over I. So if I multiply by 1 over I, 1 over I, this will be I 1 over I root 3. And then according to residue theorem, so the integral of CF of Z is equals to 2 pi I multiplied by summation R. That's 2 pi I times 1 over I root 3. I cancelled I. So our answer is 2 over root 3 pi. 2 over root 3 pi. So that is how we move from here to here. So that is all about residue and its application. So thank you for watching. Bye.